Okay, welcome everyone. Welcome everyone to another Meet the Scientist session. If this is the first time you're with us, these are called Meet the Scientist sessions, and they are a time when schools across Alaska and some of the schools in the lower 48 as well get to talk to a scientist about something that they are studying or something that they will be studying. In this case today, we'll be talking with Kelly Brunt. So Kelly is up at Goddard Space Flight Center. She's a researcher there. There she is. Hi, Kelly.
How you guys doing?
Hi. All right, Kelly, we're so glad you could be with us today. I'm Bonnie Murray, and I'm connecting from Langley Research Center. So behind me, you see our hangar. We have a huge hangar here. Langley is one of the aeronautics centers. That's the first A in NASA, by the way, if you didn't know that. And so aeronautics is a big part of what we do here at NASA, and Langley is one of the centers that focuses on that. So as I mentioned, Kelly is going to be connecting with us. Kelly's a research scientist at Goddard Space Flight Center, and you see a view of Goddard behind her. So we'll be talking more about that in just a minute. Kelly is an expert in studying ice sheets. She has developed that expertise over years and years of school and time at NASA as well, and she's currently working on the ICESat 2 mission. So today, Kelly's going to be talking to us about the ICESat 2 satellite. It just launched in September. And the exciting thing is that there is data coming down from that satellite. It's collecting data about elevation measurements. We're also going to hear from Kelly about how there's an airborne campaign, the Ice Bridge campaign, that is also collecting measurements. And so that's another verification of data. And then Kelly is headed off next week, in fact, to Antarctica to do ground-based measuring. So she's going to be talking about that. She'll be heading out on a sled. Luckily, she's in a nice warm studio today, but she'll be telling us about those 3 places that data is collected and how that's all used for verification. So again, I want to mention this is a Meet the Scientist session. These are part of a program that is run out of University of Alaska Fairbanks. It's called the Arctic and Earth Science Program. I'll show you a little bit about that at the end of the broadcast. It's one of the science activation programs that is run by NASA's Science Mission Directorate. So we say a big thank you to NASA's Science Mission Directorate for the funding that goes out to University of Alaska Fairbanks to make these broadcasts and the whole Arctic and Earth Science program possible. So in addition to Kelly connected with us today, we have 2 classrooms, and I'll be introducing them both in a second. The classrooms are classrooms where a teacher in that classroom has done some training with GLOBE. So they've learned about the GLOBE protocols, a very specific way to collect data measurements, because by collecting data in that specific way, that data can be used by scientists, researchers, other students all around the globe. And so GLOBE, global learning to benefit the environment, global learning and observations, to benefit the environment, that's the GLOBE acronym, is a training that the teachers have already gone through. And so those students that you're going to see today and meet will be collecting GLOBE measurements throughout their school year. So let's go ahead and get started and say hello to those schools. Let's go first to a school that's close to Fairbanks, and we'll say hello to Ms. DeFilippo's class. Hello, go ahead and unmute and say hi.
Say hi.
Hi. Hi, everyone. So tell us a little bit about your place. I told you that I'm connecting, from Langley, which is in Virginia, and Kelly's connecting from Goddard, which is in Maryland. Tell us about where you're connecting from.
We're here in Fairbanks. Students, raise your hands if you'd like to say something about what Fairbanks is like right now. Aiden.
Very, very cold.
He says it's very cold. Can you hear him? Did you hear him?
I can, yes. Cold, like, give me some measurements. Let's quantify that. Give me a temperature.
Does anybody have a temperature for today? Maya?
Not today, but it's been around like 10.
It's been around like 10 degrees.
Okay, that's pretty cold, yes. See, I think it's cold here today. I wore my coat and scarf, and honestly, it's 45 here today.
That's warm, right, guys?
Yeah, that's why I asked you for a measurement. Okay, what else? What's the weather like there? What's on the ground? Give me some other things.
Emerson.
There's a bunch of snow everywhere.
Speak loudly and don't cover your mouth.
There's a bunch of snow everywhere.
Wow. Awesome. How long have you had snow on the ground? A week, a day?
Elias, can you answer that? How long have we had snow on the ground?
Yeah.
2 months? Yeah, 2 months maybe. Maybe more like a month and a half.
Yeah.
Okay. All right. Is it flat there? Are there mountains? What's growing?
Trees-ish.
We have trees.
Okay. Lots
It's kind of flat here in town.
Yeah, kind of flat.
Flattish, but we have hills right outside of town.
Yeah, we have a lot of mountains.
That's not in Fairbanks.
But you can see the mountains from there, right?
Yes.
Yes. Yes. Can you see Denali from Fairbanks?
On a very clear day, if you're up high in a hill, you can get a big view of the Alaska Range and you can see Denali. But it's got to be super clear and it's pretty far.
Okay. All right. So pretty much if there's any precipitation in the near future, it's going to be snow, correct?
Absolutely.
Yeah,
Unless
not
we
rain.
get freezing rain, which has been happening more and more.
Okay. All right. So good to know. And you've got permafrost in your area, correct?
Yes.
Okay. So one of the things that Kelly and I were talking about just before we started the broadcast is that the ICESat satellite can measure elevation changes and it can measure the difference in permafrost. So I'll let Kelly, I don't want to get into Kelly's information there, but we'll share a little bit about that as we go on. Okay. Well, thank you very much. Let's switch over and say hello to Miss Bearden's class. Hello to all.
Hi.
Hi. And they're connecting from Nanwalek. Did I pronounce that correctly?
Step up.
Yes. Hi, my name is Justice Evans. We're from Nanwalek, and we're at the tip of the Kenai Peninsula.
Okay. Thank you.
Closer. Can you tell us about like the area?
Oh, yeah. We live by mountains, and across the water is volcanoes. And it's not really snowing here. Well, it did a couple of times, but there's nothing on the ground. It's mostly raining.
Okay. So you're not that cold there yet. And I imagine being near the water has a little bit of an effect on that, correct?
Yeah, it's like 30 to 40 degrees here.
Mm-hmm. Right. Because the water's not frozen. The water is still liquid, correct?
Yes.
Yeah.
Yeah. Does the water there ever freeze? Do you get sea ice there?
No.
Yeah, kind of.
Kind of.
In the lakes and yeah.
Okay. Okay, yeah. But it's not like up the north of Alaska where there's sea ice and the ships can't get through and things like that. I didn't think so, but I'm checking since I'm connected to you.
It's pretty close. Maybe 40 miles from here, they have quite a bit. Maybe it's more shallow, but they have quite a bit of ice there. But the sea ice is north of us.
Got it. Okay. All right. So what's growing there?
Who wants to share?
Anyone? Are there trees or more bushes or, what kind of things are growing there? How about, I don't know names, but how about the gentleman right there in the front in the orange sweatshirt? Are there trees? Are there trees there?
There's trees, pine trees,
Okay.
and elders.
Okay. Thank you. Perfect. Good to know. All right. Because we're going to be talking about measuring elevation of trees. So good to know that that's there. Awesome. Anything else I need to know? We're good? Okay. All right, then let's move on and let's talk about the Foursquare notes. So if you'll just turn that around for a second so that the viewers who are watching, because there are some people watching the broadcast as well. So if you have your Foursquare notes on a clipboard, just turn them around. Let's see, I'll switch back over here to Misty Filippo's class. Yeah, just hold that up to the camera if you could so that our viewers at home can see what we're doing with the Foursquare notes. Okay, so one of those boxes is where you need to be putting the scientist's name. So right at the bottom of her screen, so let me move over there. There's Kelly Brunt's name. She's pointing to it. Thank you, Kelly, for helping us out. So you want to put Kelly's name at the in that box on your Foursquare notes, and then be listening. She's going to tell you a little bit about herself, how she got interested in science, things like that. So be ready to put that into the box there about Kelly. And then there's a box where you might want to put some words to be listening for. So, for example, I already mentioned elevation. I've already talked about how we'll be using that word. So maybe put that word in there so you can write facts we talk about that relate to elevation. Another word that I quickly mentioned, but I want to go back to, is calibration and validation. All these words with the TION at the end, you know, they're very important elements of science. And Kelly is an expert in those areas. That's what she's headed out to do. She'll be headed down to Antarctica to do some calibration and verification of data. And the satellite is collecting its data by sending out photons. So put that word in there as well and be listening for that. We're going to be talking about photons and how they are an important part of this whole process. So any questions from anybody, any of the classes on how to use the Foursquare notes? Did you miss anything? Do you need me to go back and say anything again? And I'm just panning over the classes so we can check. All right. And then if not, we're going to take things back to Kelly. And Kelly, share with us, please, a little bit about yourself and the research you're doing, and take us through that work.
Hey, so I just want to say hi to everybody. I'm excited that you folks in Alaska are interested in this. This is great. My name's Kelly Brunt. I am a researcher here at Goddard Space Flight Center in Maryland. It's a little bit warmer here. We've gone over that. I'm part of the ICESat satellite mission. ICESat 2, excuse me, which launched in September of this year. Is a very precise laser altimeter. It shoots a laser beam full of photons down at the surface of the Earth. Those photons bounce off the surface, come back up to the satellite. We measure the two-way travel time of those photons, and from that we can get a very precise, very accurate assessment of the elevation of the Earth. When we come back and make that measurement again, we can tell how much our surface has changed, how much our sea ice maybe has retreated in a certain area, how much our ice sheets are actually shrinking in areas, how much our permafrost is melting and letting the ground actually sink back down, things like that. That's what ICESat 2 is all about. My component of that mission is basically ground validation. We're getting centimeter level accuracy, centimeter level precision from the satellite. We need to prove that, and we do that by using ground-based data of similar precision and accuracy. So my role is to go out and collect that ground-based data to validate the measurements that are coming from the satellite. That's basically the gist of this in a nutshell, and we'll go into some details with some fun movies along the way. How's that sound? So I think, is it now, do we start the presentation? Is that about where we're at?
I would go right into that. Yep.
All right. So you guys have seen the splash screen up for a little while, but this is just my info. Ultimately, that thing at the bottom, though, there, that at Kelly M. Brunt, that's a Twitter handle. And if you want to follow along with our campaign this year, you can actually do that. We'll be posting pretty regularly. And I think I have that repeated again at the end of the presentation, but that could be fun. So why do I study ice? Just to give you a little bit of my background, I'm a glaciologist. That means I study glaciers. And I do it by using satellite data. The glaciers that I study are really big. They're the ice sheets. Those are continent scale type things. It really takes a satellite to get at things that are about that size. Ultimately, how did I get into ice? Let's just start with this. I grew up in Connecticut skiing, and I loved it. I love the snow. I love all things winter. That kind of, and I also like the earth sciences. That's what I actually studied as an undergrad. I also raced for Syracuse University. You can see all the little stars and all the little skiers. Those are the times when I had more of an opportunity to ski than others. Some of these places get a little warm. Skiing opportunities dwindle. I did a master's degree at the University of Montana. Again, lots of skiing. And here's the most important bullet number 4. I actually worked for the USGS in Anchorage, Alaska. So I was really excited to be a part of this Meet the Scientists because I knew that a lot of you guys from Alaska are calling in. I got up to see Fairbanks. I spent a little bit of time on the Kenai over in like Homer and Seward and whatnot. So I love all parts of the state, and I'm happy to be talking to you guys today. Then I joined something called the U.S. Antarctic Program. The National Science Foundation has a program that aimed at research in the Antarctic, and I provided remote sensing and mapping support to the Antarctic Program for years. And that got me interested in the ice sheet type glaciology. I went back to school for a PhD after that. Did a postdoc at Scripps. Chicago and Scripps were the places where there's not a lot of skiing. They're the stars there, 6 and 7. There's no skier next to those. Those are the sad times. And now I'm here at NASA in Northern Maryland, so I like to run up to Pennsylvania and go skiing quite a bit. So I think it's really playing in the snow that got me interested in glaciology. So the satellite we're on is called ICESat 2. Ultimately, why are we interested in changes in our ice sheets? The graphic you're looking at is showing the changes in Greenland ice mass through time. And you can see, you know, there's a little bit of seasonality to this. The plot goes up and down like a little seesaw throughout the years. But the general trend is down. The Greenland ice sheet is losing mass. And you can see it's losing most mass around the edges. And that's where the ice sheets are in contact with both our warming atmospheres and our warming oceans. And the same story, although not as extreme, is happening in Antarctica. Again, there's some seasonality to this graph, but the general trend is definitely down. We are losing mass in Antarctica. And again, it's happening where our ice sheets are in contact with both our warming oceans and our warming atmospheres. Now, when we lose that mass, it goes right into the ocean and it affects mean sea level. And a lot of the fringe around Alaska is pretty steep, and sometimes, you know, millimeters of sea level rise don't make a lot of sense to you guys because you probably can't see how you would feel it. But there's other changes happening too. Sea ice cover. We're losing some of our sea ice cover, and that has a global impact on weather patterns. So there's a whole bunch of changes in the polar regions that are extremely meaningful for sea level rise in our coastal communities, but other changes that are also very important to a global community with respect to weather. And here's a great, you guys are actually in this animation here. This includes Alaska, but this is the spatial decline in our sea ice extent. And we hear about this on the news every September. Every September they come in and they show us a new map of what we call the summer minimum of sea ice. And it's generally lower than it was the year before. Again, you can see some spikes in this data set. We call that interannual variability. But the overall trend, you can see from the left side of this graph versus the right side of this graph, the general trend is again down. We're losing our sea ice extent. That's important, but what really keeps our sea ice scientists up at night is this graph, or this animation. And this is kind of a long animation, so we can talk about this a little bit. But what this is the change in sea ice thickness through time. Thickness and age of our sea ice pack go hand in hand. Thicker ice is older ice, thinner ice is newer ice. The really white hot spots of this animation, that's our thick old ice. And what you're kind of seeing over time, and I think we're up to about 1994 right now, but what you're seeing over time is that bright white is diminishing, which means we're losing our old thick ice. And in this map representation, that ice represents something that's like more than, say, 4 or 5 seasons old. You can't make 5-year-old sea ice in a year. So as we lose this, it's harder and harder and harder for us to replace this, this old thick ice. Thin ice, the new stuff, is also really easy to melt. So that's not going to stick around for seasons, or it's very hard to get it to stick around for seasons. And you can already see the sort of impact this is having. Much of the ice is kind of, the old thick stuff is actually moving down towards northern Canada and Greenland. But for the most part, and the take-home message here is we're losing our super thick ice. This is almost to the end. It's a good video, but it's a little long. And just in case you forgot what it looked like in the beginning, this is September from, I can't quite read that year, September from like
1984.
Thank you very much, to roughly 2016 maybe. And this is September versus September. I'm comparing apples to apples here. I'm not doing anything kooky. And you can just see the difference over time.
So just for reference, students, just raise your hands. You don't have to unmute. How many of you were born after 1984? How many of you were not even alive in 1984? Right. Yeah. So that measurement goes back before you were even alive to now, and look at that change that's happened in that time. Wow, thank you.
So with these two sort of stories in mind, the loss of our ice sheet mass contributing to sea level and the loss of our sea ice, as we lose our sea ice pack again, that changes what we call the heat exchange between the ocean and the atmosphere. And when you change that dynamic, you have an influence on global weather patterns. So both these things together affect the global community, not just the coastal community, and that's pretty important. So with that in mind, we were able to develop a satellite that addresses these issues. And I know the video starts in suburbia somewhere and in trees. And that's because ICESat 2 is not only looking at our polar regions, but it's also looking at the whole world and making other measurements. The ones that we sort of talked about before, trees in your backyard, or maybe changes in the permafrost.
ICESat 2 adds
and this is a nice little animation here that's just
from ICESat
kind of talking about the measurement strategy and how we're set to do things.
Or in land.
ICESat 2 is designed to measure the changes that are going on in the cryosphere, in the polar regions.
All the change is at the edges. Those are the steeply sloping parts of the glacier that interact with the ocean, and that's where all the action is. That's where all the mass is being lost.
In order to estimate the mass changes, we need to know the height of things. The mission ICESat 2 carries a single instrument. It's called ATLAS, the Advanced Topographic Laser Altimeter System.
ATLAS sends out small pulses of laser light 10,000 times a second. And by measuring precisely how long it takes that light to go from the spacecraft down to the Earth and back up to the spacecraft, allows us to figure out what the height of the surface is beneath ICESat 2.
We need to measure the time of flight of a single photon or a single laser pulse with a precision of a billionth of a second.
NASA engineers had to come up with entirely new ways of measuring time very precisely.
A billionth of a second translates to an elevation change precision of just a few centimeters. Climate change is amplified in the polar regions. ICESat 2 is designed to measure those areas and will help us to understand what's going on with our planet.
Awesome. So I just want to point out one thing. Nobody does animations of this type better than NASA. And if you look at almost any earth science, if you have any sort of earth science question, I encourage you to log on to NASA's SVS. I think it's Science Visualization Studio. Type in the search bar, anything you have that's kind of earth science related or even space science, I'm sorry, and see what type of animations they have, because nobody does it better than NASA. And I almost guarantee that whatever you're looking at, you can find an appropriate animation on the NASA website. It's fantastic. It's a great teaching resource.
So that's something you might want to jot down on your Foursquare notes. Sorry to interrupt you, Kelly.
No, that's perfect.
That's the SVS. Your teacher probably showed you a video of Kelly to get you ready for this, and that was a video off of the SVS, the Science Visualization Studio website. So that's a good place when you're doing your homework, if you need to research, something like that, the NASA SVS. And you can Google that, and that'll come up, and you can search for videos there. Thanks, Kelly.
No worries. So because, we've got these two concerns in the polar regions, plus we want to collect a global data set, we were able at NASA to develop an instrument, ICESat 2, and it launched September 15th is what I have in my head. That might be a little bit wrong. It's been a whirlwind of a couple months, but it was so exciting. And I want to share with you guys the video of the launch, because this is also another thing we do really well. We launch stuff. So here's the launch video.
8, 7, 6, 5, 4, 3, 2, 1. Liftoff of the final Delta II, launching nearly 3 decades of science research and exploration missions, lifting ICESat 2 on a quest to explore the polar ice sheets of our constantly changing home planet.
Now 27 seconds into flight. 30 seconds in, Mach 1, Delta 2 is now supersonic. Continuing to see good chamber pressure on the RS-27, both linear engines as well. Seeing consistent fuel and oxidizer injector pressures as well. And at T plus 46 seconds, max Q, maximum dynamic pressure. And at 57 seconds in, we have web burnout on the solid rocket motors, seeing good responses. And we have burnout on all 4 motors. And Delta will hold on to those motors for an additional 20 seconds prior to jettison. Now 1 minute, 20 seconds in, standing by for motor jettison. And we have good indication of jettison of all 4 solid rocket motors.
Cool. So that video runs all the way out to what we call the second stage. And when that happened, when we hit the second stage, there was so much relief. Rocket launches are kind of fun, even at 4 or 6 in the morning, whatever it was. We all had a good time, but everyone was very excited about getting to the second stage. So we launched in the middle of September. Now we're at this point where we're actually looking at data. And so this next slide has the different type of surfaces that we've been able to tease out. So in the upper left, there's an ice sheet surface, clear as a bell. Just below that, there's a sea ice surface, and that has leads where the sea ice has separated a little bit, usually based on wind and a little bit of surface current action, and created a open water between the sea ice packs. And then in the whole right panel is, believe it or not, that's a tree canopy. So you're seeing the ground surface underneath and the canopy of the trees above. So again, we expect to have centimeter level accuracy and centimeter level precision for our data that we get from ICESat 2. How do we prove that we've got centimeter level accuracy and centimeter level precision? So what you're seeing right now is an example of about a day or two's worth of ICESat 2 tracks. And what you can see is they're kind of spread out at the equator, and you can kind of see that they converge up at the poles. They don't quite hit the pole, but they get pretty dang close. Ultimately, if you look, you can see a pretty dark green circle developing at the North Pole, and there's one at the South Pole as well. And we're not going to let this entire movie evolve, but I just want to point out there's about 1,387 unique ground tracks associated with this satellite, and we go to 88 South and 88 North. And what that ends up looking like is this. So that's what the center of the Antarctic continent looks like, with what we call the pole hole, that data void in the center right at the pole. But look at how green it is right around that pole. That's where the ICESat data are most dense, because all the tracks are converging in that area. So if you kind of look towards the edge of the image, you can see the tracks are spreading out at the equator and they're tight at the poles. So if I wanted to, say, look at 20% of the ground tracks and I wanted to look at the equator, I'd have to drive quite a ways to get that, to look at the 20%. I'd have to drive something like maybe 8,000 or 10,000 kilometers. If I want to look at 20% of the ground tracks at the pole, I only have to drive 300 kilometers. So that's what we did. We actually flew to the South Pole. You fly commercially to New Zealand. Then you fly to the edge of the continent to a place called McMurdo Station, which is a very large research station, about 1,000 people. Then you fly all the way into the South Pole. And then from there, this is crazy. We got in these tracked vehicles. You're going to see a wicked cool movie in the next frame. But we got in these tracked vehicles, and then we drove away from the pole to drive that little wedge shape that you see in the upper right corner, that little piece of pie. So we started at the pole, then we drove counterclockwise back all the way around to the pole. And you can see in the lower right, that's actually the South Pole, the little dome, or globe rather, that marks the South Pole, and our entire research group of four people for 2 weeks and 2 vehicles. Our entire research team pictured in that. Okay, so here comes the next video. This is like my favorite video. About this is they said, okay, we're going to have you set up your tents and just leave them set up and drive that whole pie piece, that whole 750-kilometer pie wedge with your tents set up. And I thought they were crazy, and look how well it worked. No one was more surprised than me. It was very exciting. And here's some point of view shots. This is I'm actually sitting on the right. The mechanic, the most important person on the Traverse, is on my left. And the other vehicle, we were 4 people, so 2 per vehicle. The other vehicle's in front of us, and you'll see in a second, we're actually one vehicle's gonna cross the path of the other. And what that's doing is it's helping us with statistics. We're basically gonna compare one vehicle's data versus the other. what are we actually collecting? We're actually collecting GPS data. So a lot of you guys probably have a GPS navigator in your car. That's probably accurate to about 3 to 5 meters. So you know kind of exactly where you are when you're driving to just a handful of meters. If we take our data home and we post-process it, we can get down to the centimeter level. And that has to do with the way that we're sampling it, the things that we're muting out, and the delay that we wait before processing the data. But we can get down to the centimeter level, knowing exactly where we are. And as important, you know, we know exactly where we are, but we also know exactly our precise elevation. We can get down to centimeter level elevation. And that's pretty cool. That's what we're going for. So now with our GPS measurements that we're collecting the whole time, we know exactly where we are in XY space, and we know the exact elevation to compare against the satellite. And it's beautiful out there. I don't have to describe to you guys how beautiful kind of sometimes the flat white is, or even the cold, or but it's absolutely lovely to see this type of horizon, which I think is really cool. The other things that we get to see on this this trip are sundogs. I'm sure you guys have seen sundogs up in especially you guys up in the Fairbanks area. In the lower left in this image is a shot of us gassing up. This is a gas station / rest area that we've set up in the lower left. And on the right, this kind of just gives you a sense of some of the worst weather that we had. Wind is really the only thing that plays a role in affecting our weather and temperature on a day-to-day basis. Here's some kind of life on the road trip type photos. In the upper left, that's our very tight kitchen tent. It's a little crammed. You couldn't even get 4 people in the photo. In the upper right is our whole traverse group at the end of the actual data run. Lower right is us fueling. It was a total team effort. And in the lower left is, I have to remind people, it's effectively a road trip. So we ate junk food the whole way. It was pretty bad. But that's beef jerky and maple syrup packs. And this is kind of fun. In the upper left, I'm taking a video of the 2 vehicles rolling out. And the first thing I want you to notice is on the back of that piston bully is a little antenna sticking up. That's our GPS antenna. And then you see, look at how well that sled is running. It's just amazing to me. I'm still shocked. I was there, but I'm still shocked. And then the other sled starts to roll out. The sled that just went by had a lot of sleeping tents. This sled that's coming up has 1 sleeping tent. And then the big tent that you see in the back is the kitchen tent. And everyone always asks, how did you go to the bathroom out there? The tent behind the kitchen tent is a little bathroom tent. So 2 weeks of that. That was rough. So now what's going to happen in the lower right is now there was a GoPro on the back of the first sled. And you're going to catch me now left on the ice sheet. Now, in a second, I'm going to start running. I'm going to start running after that vehicle because I don't want to be left there. It's very cold. And it's a very scary prospect to think about being lost or left behind. I don't run for much, but I certainly ran to catch up with the vehicle. It was just kind of fun seeing the 2 perspectives there. Is there audio here? I can't remember. So the other cool thing that's going on right now is we just finished an aircraft campaign. Bonnie showed you the graphic with the ground base, the airborne, and the satellite component. This is a short video just showing you some highlights from the airborne campaign, the airborne component of that mission. They just returned the other day, last week, from a very long Antarctic campaign. IceBridge is a pretty impressive mission in and of itself. It's basically the largest airborne operation ever undertaken by NASA, no matter how you sort of measure it. Lots of aircraft involved, lots of people involved, lots of scientists, lots of instruments, and it's pretty exciting. I think we're coming up to the end of this. So what we'll ultimately end up with is the satellite data, as we were pointing out, collecting elevation data. The airborne component in between, also collecting elevation data. One of the other cool things about IceBridge is not only does it have altimeters, laser altimeters on it, but it also has radars on it. And the radars actually allow you to see into the subsurface, which is nice. That's not something we get from the lasers. And what does that look like on the ground? The components here that you see, the big round circles, the ones that are kind of almost a full frame here, those represent the airborne footprints. And that small this set of circles right here in the middle, this is also, there's two spinning altimeters on the aircraft. So this big circle right here and this little set of circles right here, that's from the airborne component. This is from the satellite. And then this squiggly line is us not being able to navigate right. This is, that's the ground-based component. And this is what we hope to be able to directly compare, the ground-based versus the airborne versus the satellite. And that's that awesome graphic ready for publication that hammers it home. And you can see in here, there's two things that you can follow. One is this @NASA ICE. That'll keep you updated with respect to both ICE Bridge, which just ended, and ICESat 2 updates. And then the other one is this one down here, where I'll also be posting regularly about our campaign to the Antarctic. And I think we took the video out of that one. Yeah, perfect. So anyway, so that gives you an overview of what we're doing. And at this point, I think we're opening it up to questions and comments from the students, correct?
Yes, that's correct, Kelly. Thank you so much. I want to say thank you first. That was great. I love the way you represented the data. I imagine students have to make graphs once in a while, and it's really nice to be able to see how other scientists use those graphs and things like that. So I encourage you to remember that when you're making your graphs and as you collect data. So let's start with Ms. DiFilippo's class. And there we go. I see you writing down some notes still. That's great. Is there anything you want to know more about, first of all, or do you want to ask Kelly something completely different? Like more about how she got interested in science or what she's going to wear when she goes on this next trip next week? Like, what would you like to know?
Okay, I'm unmuting you. Anybody have a question? Aiden and Kaylin, and are you raising your hand?
Awesome. And just tell me your name before you start.
Right, so I'll call on a student. Let me know if you can't hear them.
Okay.
Go ahead, Kaylin. What's your question?
Nice and loud.
Okay. Next person. Let's see. Eli?
Someone said that they like.
I can't hear. That's why I was saying, just yell it out.
Yeah, so we'll repeat it for you. Go ahead and yell it out.
Perfect.
Said that they like ice skating. Like, y'all get hurt while
Do they get hurt while, like, what, ice skating or skiing? I'm curious about your interest in skiing. Did you ever get hurt?
Nothing catastrophic. I used to ski race, so you kind of run into plastic gates a lot, and it definitely leaves a lot of bruises. Nothing that wasn't fixable.
Very good. Okay. Great question.
Did you remember your question, Kaylin? Go ahead.
In Antarctica, have you ever seen like polar bears or like penguins?
Did you hear that question?
I did. And I made a huge mistake today. You should never present a polar presentation without at least one picture of animals. I've seen a lot of, in the Antarctic, they have penguins, and they're pretty much unique to that part of the world. So I've seen quite a few penguins, Adelies, emperors, gentoo penguins. I've seen a lot of seals as well, like Woodell seals. They kind of look like dogs. They're so cute. Elephant seals, they stink. They're very big and they stink. I saw one leopard seal by a big boat. So you see that. I've seen whales. With the, looking at ice sheets, you also tend to run up to Greenland as well. And on one of my trips to Svalbard, we saw a polar bear in the very distance. And keep in mind, polar bears are, as you guys know, they're northern hemisphere. So, there's a bit of wildlife. There are parts of Antarctica that have more of it than others. When we fly into the South Pole, one thing I didn't bring up is that the South Pole is actually 10 to 11,000 feet above sea level. So the animals that are on the coast generally don't make it all the way into the South Pole. So we see very little wildlife once we're away from the edge of the continent. Great question, though, and I apologize for not bringing animal pictures. It's my mistake.
Well, we're going to expect you to put some. We're going to follow you on Twitter. So
Perfect.
All right, let's take one more. We'll come back to you, but let's take one more now, and then we'll go over to Ms. Bearden's class, and then we'll come back.
Okay, go ahead, Imani.
What did you guys have more than one sleeping tent, or was it really, or did you guys all have to sleep in there? It was really crowded.
That's a great question. So on the back of there were 4 people on the Traverse, and we each had our own sleep tent. But let me just, one of the reasons why is that we put about 4 thermarests down, and then we put big minus 40-degree sleeping bags on top of that. I take my minus 40-degree bag and I shove it inside another 0-degree like rectangular bag. So by the time all is said and done, when you're standing up next to your sleeping bag, everything is about at your knee level, and it's, you know, there's just stuffing everywhere, so it takes up a lot of space. So we all had our own tents for, you know, both privacy, sanity, and because of space. So it's actually, it was really, really comfortable, actually. That's a great question.
Thank you.
Awesome. Okay, so let's go over to Miss Bearden's class. So questions from Miss Bearden's class. Now you're a little closer to water, so you can get a feel for what sea ice might be. I think that's a little harder in Fairbanks where they don't have sea ice near them. Okay.
Go ahead, Justice.
Go ahead. Come on up and ask your question.
Is the Antarctic affected just as the Arctic?
Can someone repeat that question? I'm sorry.
Or just say it again. Yeah, just say it again.
Is the Antarctic affected just as much as the Arctic?
Is the Antarctic affected as much as the Arctic? Do you see a difference in how one is affected over the other?
Man, that's a great question. We're definitely seeing bigger changes in the Arctic than the Antarctic. You know, our ice, you saw the very first 2 slides with the mass loss, the Greenland ice sheet lit up a little bit more than the Antarctic ice sheet. One of those reasons is that most of Antarctica is south of like 65 degrees or, you know, almost 70 degrees. Most of Greenland is actually below that, right? Greenland doesn't reach all the way up into the very polar regions. So some of the latitude arguments, you know, as you get closer to the equator, it gets warmer. So we see far greater changes in our Greenland ice sheet than we do in the Antarctic ice sheet. Another contributing factor there is just pollution coming off of North America going right at the Greenland ice sheet. So it's a great question on the ice sheet side. Sea ice is a little bit more complicated. We're definitely seeing amazing losses in our sea ice in the Arctic. We're not seeing the same type of signal in the Antarctic. The Antarctic sea ice signal is extremely complex. Probably not something I want to dive into at this level. I do think the changes in the sea ice are greater in the Arctic than the Antarctic, but in regions, some of the Antarctic sea ice is growing, and yet that's still an indicator of complex but probably warming environment. So I think that the changes we're seeing are certainly greater in the northern hemisphere than they are in the southern hemisphere. The Antarctic Peninsula, which reaches up toward South America, that's where, you know, the latitude of that continent is closest to being equator-like. It's not. It's way down at like 55 degrees. But in that region, there's a pretty big hot spot where we're seeing amazing changes. But you're absolutely right. For the most part, the major changes are in the Arctic.
Mm-hmm. And also remember, what happens in the Arctic does not stay in the Arctic, right?
That's
what
right.
happens in the Arctic affects the entire globe. Yes. So great
Absolutely.
question. Good point to understand. And then we'll be looking at how that's affecting everywhere else. Yeah. All right. Any other thoughts, questions? Okay. Someone in the back. Do you mind coming up to the front to ask your question? Would that be okay? And tell us your name because we haven't met you yet. Thank you.
Hi, my name is Charlie, and I'm wondering, are you guys planning on making more ICESats?
That's a great question. So ICESat, the predecessor to ICESat 2, was operational between 2003 and 2009. We just launched ICESat 2 in 2018, so there was a tremendous sort of time gap in between that we've kind of covered with IceBridge. We bridged the data gap between the 2 satellites with that aircraft mission. What that's done is given us an amazing time series of laser altimetry, especially in the polar regions, going from 2003 now all the way to 2018. We expect to get, we have a mission requirement of 3 years for ICESat 2, but the current best estimate on fuel and longevity of the lasers and all that good stuff, current best estimate is that that's going to probably be more like 10 years. So now to plan a satellite and whatnot, you need a lot of lead time. So of course, people are already thinking about the next measurements that would be made after ICESat 2. And of course, there's lasers involved there. And there's many ideas of how that could be accomplished. My gut sense is that it won't be called like ICESat 3, and there'll be added capability to this, to the next generation of, whatever it is. But because satellites are so hard to launch and so hard to put together, and it takes a lot of checks and balances, of course, we're already thinking about that. What's the next measurement that we're going to be making beyond ICESat 2? So nothing in concrete, nothing in stone, but a lot of people thinking hard about that right now. Great question.
Mm-hmm. I want to mention also that if you're thinking that building a satellite might be fun, there are other satellites being launched, and in fact, other satellites landing. So trivia question, do any of you know the name of the satellite? Well, it's not a satellite now because it landed. Do any of you know the name of the rover that just landed on Mars yesterday? Okay, trivia question. Anybody over in Ms. DeFilippo's class? Just checking.
I feel like I heard.
ICESat.
Yes.
Yay! yes. So that's an interesting satellite to look at. That one is going to be able to look down into Mars a little bit. It's the most recent satellite to land on Mars, or excuse me, rover to land on Mars. Satellites go around things, and that's where Kelly showed you that the satellite is in a polar orbit. It's going from one pole down to the bottom and then back up to the top again. But we also have sent several rovers to Mars, and the newest one is ICESat, and it just landed. So if you didn't see that video, that's a good video to catch up with and watch as well. And there's always satellites being built and being looked into. So any other questions from Ms. Bearden's class? Okay, we're going to go back over to Ms. DeFilippo's class. Any other questions there?
Okay, so, we're back to questions. Hey, I just want to let you know, Bonnie, we have about 5 minutes before our lunch recess break.
Okay, I thought we had 10, but thanks for letting me know.
We can have, at noon, yeah. So they need a minute or two before.
Absolutely, and recess is important.
But we do have multiple other questions.
Okay.
So, Aiden, go ahead.
Miss Kelly, what is the rest of your email for the ICESat 2?
You want her email address?
Mm-hmm. Yep. So they didn't get that in their notes. Maybe our producer up there at Goddard can put that slide back up for us. Thank you for asking.
Or you can email it to me.
Absolutely. Yeah. But I want to let the students get that in their notes as well.
About science for the scientist. Go ahead, Shady.
Yeah.
There we go.
I was going to say how much people there were on the trip.
I can't hear it. Say it louder.
Loudly. Ask her loudly. How many people?
How many people were there when you had the trip to Antarctica?
Yeah, so when we were driving, it was only 4 people. When we were at the South Pole on station, that station has approximately 200 beds for people. And when we were along the coast in McMurdo, that has about 1,000 beds. So we went from 1,000 people down to 200, down to just 4, and then back out. Good question.
All right, James.
When you were in the
I don't know.
In the tents?
In the driving in Antarctica?
Yeah.
Yep. Okay.
When you were driving in Antarctica.
Loudly.
When you were driving in Antarctica, what did you do to dispose of your garbage? Like, where did you put the garbage?
Yeah, that's a great question. We bring it all out with us. So any trash that we make, we have we separate out our recyclables in transit. We put it in trash bags and carry it out. For the most part, honestly, we didn't make too much trash. It was just the trash from making food, mostly in the evenings. And you saw all the snacks, the beef jerky wrappers. not a lot of trash.
Yeah, that sounded pretty fun. And we're going to put the email back up. I love the fact that you want to take notes. So I'm going to leave that there and go ahead and ask another question. Someone in Mr. Filippo's class.
Antonio.
In Antarctica, does it get warmer or colder there?
Oh, a lot colder. So you guys said it was about 10 degrees where you are. Where we were, it was about -10 all the time when we were driving. A little bit colder than that, actually, like minus 14 or so. So a little bit colder. And keep in mind, we're there in the summertime. So you can imagine what the wintertime looks like. The wintertime's even colder. Part of the contributing factor there is because Fairbanks is very cold in the winter. But part of the contributing factor there is that the altitude. They're at 10, 11,000 feet above sea level, which keeps it cool as well.
Okay. I mean, I still got hands up.
Keep going.
Let's take two more. Two more.
How much money did it cost to build the rover on Mars?
The rover? I don't know the cost on the rover. I can tell you about ICESat 2. ICESat 2 is about $1 billion to
$1 billion?
One, yep, B with a B.
Yeah, yeah. So, very important to be able to do that verification. We really didn't get to that. What does verification mean? How do you, what does that mean? Any thoughts on what that word means?
Verification.
Like a type of test.
What do you think?
They don't know. So they're comparing ICESat data with the ground data they take when they're like driving around Antarctica. Do I have that correct?
Perfect.
You do.
Absolutely.
How about in the class? Any ideas on verification? Have you ever had to verify data?
Say
What do you think?
I don't think they really grasp that.
Okay, so how about in Miss Bearden's class? What does it mean to verify something?
Check if it's real.
Say it louder.
He said to check if it's real.
Okay. And you know where you've probably done this? Did you ever look something up on the internet and you're like, is that really true?
All the time.
All the time, exactly. And so how do you know if that's true? You look it up again and again and again, right? How many of you have done that? Anybody in Miss Bearden's class done that? I was thinking you might have, yes. So that's the thing. You got to do the repeated trials and you got to get it from you've got to go to several different places and look. And so that's what, am I getting that right, Kelly? That's what you're doing.
It's perfect. It's perfect. We have better confidence in, at face value in the data that we collect on the ground. So we use that as the truth, the ground truth. And then we just compare satellite data against it to validate that the measurements we're getting from the satellite are the same as what the ground base were. And that's where we make the verification.
Right. So for example, students in Fairbanks, I'm coming back to Ms. DeFilippo's class. If you were measuring the change in the surface due to thawing of the permafrost, then we could compare what the satellite readings, what we're getting from the satellite readings, and we would be able to verify those satellite readings of the elevation. So that would be a really good exercise to do. And I think I might have earlier used the wrong word. And even if I didn't, just to clarify, permafrost does not melt. It's kind of like a steak that you would put out on the counter. It thaws out, but because it's not all water, it's a lot of soil as well, permafrost thaws. So we could measure that thawing and the changes that has in elevation. I know when I was in Fairbanks, I saw some houses sinking. Anyone in Ms. DeFilippo's class seen any evidence of that? Like houses or roadways sinking? Anybody? Yeah. So there are changes in elevation due to the permafrost thaw. Yeah. Okay, well, I'm going to show you just one activity as a resource to close here. I think I am, yes. Do we have another question? Is that what you're telling me, Ms. DeFilippo? Okay, I wasn't sure.
Oh,
okay. All right.
Can we ask one more question?
I'm sorry, I had you on mute. No, we don't have any more questions.
Okay, great. I want to show you, in closing, I'd like to show you, there we go. This campaign, it's called Trees Around the Globe. You mentioned there's trees near you, and students in Ms. Bearden's class, you said the same. So there's a campaign right now where you measuring the height of trees, which is a great math exercise also, good to brush up on your math skills, and that allows you to send that data in and be another source of verification for the ICESat 2 satellite. So I'm showing you the website here. I think I've already sent it out to the teachers. If not, let me know. I will make sure you have it. And that's a great way for you to be a part of this verification that Kelly will be doing. So I'm going to close there. Let me just try and unshare my screen and stop presenting to you. Here we go. Okay. All right. So Kelly, I want to wish you, let me make your picture large there. We want to wish you well on your trip. Dress warmly.
I will.
And take some really good snacks. And maybe we'll connect with you again when you get back. How long will you be there?
6 weeks total. 2 weeks in the vehicle, but 6 weeks to travel and get set up.
Okay, and get over there. Wow. All right. Well, we thank you so much for connecting with us today. I'm going to go to each class. If you could just do a wave and say thank you to Kelly for connecting with us.
Hi,
Thank you. All right. Thank you so much, Kelly. I appreciate. Thank you, classes, for connecting. I hope you have some follow-up questions as well. Send them to me or Kelly, and we'll get answers out to you. Bye-bye, everyone.
Thank you.
Bye.